Hello all, welcome to the tutorial sessions on photonic integrated circuits. So this is week 4 and uh, we will be reviewing how we got the mode solutions or the solutions for the value of the propagation constant beta for an infinite slab waveguide in the class, and then we will be doing a problem for like we'll see the solutions for one particular case, like an example problem. So first of all, what is an infinite slab waveguide? Infinite slab waveguide is basically when we have the refractive index confinement only in one direction. So here in this case, you see, uh, we are saying the cross section. NF is the film refractive index, NC is the cladding refractive index, and S is the substrate refractive index. And then this film extends to uh, infinity in the z direction and in the y direction. So the confinement is there only in the x direction. The height of the film is given by h, and as we know, for this slab waveguide to to uh, to guide light, it is required that NF is greater than both these, right? NC and NS. So in general, NF will be greater than NS, will be greater than NC or equal to. So these both can be greater than or equal to. Okay. Right. So I hope you understood why we call it an infinite slab, because we are not assuming it to be for some finite value of z or y. So we are assuming that it is for infinite z. So this is not a real world case. It's just a say the closest thing that can come in real world to this is if I have a waveguide that is very thin but flat, in the sense if I'm seeing the cross section of the waveguide, so say this is the y direction, this is the x direction. So in the x I can see a confinement, so this is NC everywhere. Here it is NS, and so in the waveguide it is NFIL, NF. So if I have a very thin film, and so obviously there will be an end to the waveguide in the real world case, but the thickness of the film is very small compared to the width. Such a case is also called as a slab waveguide. So to simplify this case, we say it is an infinite slab waveguide. So now we need to worry only about the confinement in the x direction. Okay, so say my light, the refractive index confinement is only in the x direction, and my light is propagating in the z direction. Say the light is going in this direction, in the z direction. So how will the light travel in the z direction? Obviously, it will keep. So this is, if this is my k vector, it will keep hitting the boundaries, and it will be traveling like this. So it is not necessary that the k vector will be directly pointing in the z direction. It can have some x component. The idea is that it will hit at the boundaries, and then there will be total internal reflection, and it will be bouncing back and forth. Okay, so say this is my k vector as it is shown here. This is the k vector. Now k vector denotes the direction of propagation of light, right? So if my direction of propagation is in this direction, then my h, that is the magnetic field and the electric field, will be perpendicular to each other and perpendicular to the direction of propagation, right? So then there are two possible cases. One case is when electric field is pointing outside the plane. So this is my xz plane. My electric field is pointing outside the plane, and magnetic field is pointing in the xz plane. Second possibility is electric field is in the xz plane and magnetic field is perpendicular to xz plane. So either electric field will have a y component, only y component, E equal to Ey, or we will have H equal to Hy. So basically, they don't have any x and z components. So if you just think about it, you will understand that these two are the only two conditions. So we cannot have both electric and magnetic field in the xz plane at the same time. Otherwise, they won't be perpendicular to each other, right? Um, yeah. So the case in which the electric field is perpendicular to the z-axis. So my net propagation, light propagation is in the z-axis, right? Even though at a particular instant it is propagating in some other direction, but the net direction of the guided wave is in the z-axis direction, right? So if my net propagation is along the z-axis, then uh, then then transverse electric polarization is defined to be the polarization in which the electric field is perpendicular to the z-axis. So that means the electric field is in the uh, is along the y-axis. So like in this case, if it's along the y or negative y-axis, then we call it transverse electric polarization. If the magnetic field is along the y or negative y-axis, then we call it transverse magnetic polarization. So yeah, and we can also have a combination of these two. Right. So that was about polarization and how we define transverse electric and transverse magnetic. Right. Uh, so for the case of finding the modes of a slab waveguide, we will first find the transverse electric modes. So at the time for starting, we will just find the transverse electric modes. So then that means that we are assuming that electric field is polarized only along the y-axis. Okay. Um, right. To solve, let us make some more. Let us write down some more things. So the source frequency, let us say it is omega naught. That is the frequency of the source. Then then can we write down the wave vector in vacuum? So say so if the frequency of light is so much, and say it's not traveling in a medium, it's just traveling in this particular light is traveling in vacuum, then the wave vector, I'll write it as vacuum wave vector, we'll denote it using k naught, and k naught will be nothing but omega naught upon c. So it's a vector, so I'll write it as the magnitude of k naught is nothing but omega naught by c. Fine. Till here it's okay, right? Okay. So now to find the solutions in these particular boundary conditions, uh, we need to write down the wave equations in these conditions, right? So to go about it, um, let me just remind you the equation of electromagnetic waves that we had found out earlier was right. So now this EY, how is this EY changing? So obviously, since the EY is pointing in the y direction, however, there is no field confinement in the y direction. So EY does not depend on the y. So even if it's way too much in front or too much behind the paper, it will still have the same EY. So what EY depends on is uh, basically uh, the propagation, that is z. So it is a wave, right? So it will change with the z coordinate and the x coordinate. So I can write this down, EY as EY of x comma z. Basically it will depend on x because it depends on whether it hit the boundary and reflected back or not, and it will depend on z because it is varying periodically also with z. Okay, so EY will be EY of x comma z, and there is also a periodic component with time, e power I omega t. Then if I just substitute this into this, then what will I have? So I'm not substituting for this part, so this part I'll leave as it is. uh, Minus, I just want to simplify this dou square ey by dou t square part. So here if I put this, then dou square ey by dou t square will be nothing but omega naught square. So this will, I'll write it as omega naught square, right? And because there is an I that will come out twice, so there will be a I square, that is -1. So this will become +1 into mu epsilon times, obviously this ey will still be there. So we did nothing, we just double differentiated this. So we did dou ey by dou t, that will be nothing but I omega naught ey e power I omega naught t, and then we did a dou square ey by dou t square, that will be again I omega naught square ey e power I omega, same thing. Okay, so then this is nothing but ey, like I'm just denoting it like this because I ended up using the same way here. So this ey is this, and I omega naught square is omega naught square into -1, that will make this +1. Okay, so from this I can write it as del square ey, sorry, plus omega naught by Vp. So if you remember, Vp is nothing but 1 by root mu e square ey equal to 0. So till now we did nothing but just simplified the wave equation for electric field. So since we are assuming the transverse electric modes, so it becomes easier for us. Now we don't have to worry about uh, electric field having multiple components, because now electric field only has the y component. So this is the wave equation until now. Okay, sorry, I'll just write it down again here. Del square ey plus omega naught Vp square ey equal to 0. Now what is omega naught by Vp? We can even further simplify this and simply write it as del square ey plus k naught square n square. N is the refractive index, and I just put it as Ni because we have not specified whether we are solving in this region, or this region now. So for now I'll just put it as Ni. This Ni can be either film refractive index or cladding refractive index, anything, right? So this will be Ni square. K naught Ni is nothing but omega naught by Vp. So by now you are, I think, familiar with these equations, right? Ey is equal to 0. Uh, just in case you would have forgotten, I'll just write it down. K naught is nothing but I need to take a different K naught is omega naught by C, and omega naught C is nothing but okay, refractive index is C by Vp. So C is n times Vp, right? So I'll write it n times Vp. So K naught is omega naught by n Vp. So that means omega naught by Vp is nothing but n times K naught. So that since it's square here, I'll put a square here. So this is my final wave equation until now. Now I have to write this for different refractive indexes. So I have 3 different refractive index, and for these 3 different regions, I'll get 3 different solutions for this same equation. Now, as I said, this Ey is a function of x and z. But we can simplify this even further by noting that in z direction, it will only vary periodically because it's propagating uh, along the z-axis. So, we can actually write this Ey of x comma z. So that is the magnitude of this, and then there will be obviously a time component also, but we can write this as Ey of x e power I beta times z. Okay, this is because the intensity will be varying, or the amplitude of the wave will be varying periodically along the z-axis with a period of beta. Okay, so now if I substitute this into this, what do I get? So then I will get, so now Ey is nothing but Ey e power I beta z. So then I'll just, this del square is nothing but dou square by dou x square plus dou square by dou y square plus dou square by dou z square. Dou square by dou y square is 0 because we are assuming Ey is not there, not varying with the y axis. So we are left with dou square by dou x square of Ey plus u plus um, plus what will be dou square by dou y square, that is 0. What will be dou square by dou z square? Dou square by dou z square will be nothing but I beta square Ey of x, correct? And then I have this term also plus k naught square ni square Ey of x comma sorry, not x comma z, I'll write it at Ey of I don't sorry, this I made a mistake here. So even after double differentiating, it will still be Ey of x comma z. Right, because when I double differentiate this, I'll get what? Ey of x e power I beta z into I beta square. So that is the dou square Ey by dou z square term, right? So this is nothing but I beta square Ey of x comma z. So this I made a mistake by writing it as just Ey of x. So I am correcting it now. Um, right. So we have come till here. So this is equal to 0. So basically I'm just writing down this by putting I'm just substituting this in so if I call this 2 in 1, by substituting 2 in 1 I get this, and further simplifying I'll drop this x comma z term. I can just write it as ey plus k naught square ni square minus beta square, because I square is minus 1, ey is equal to 0. So finally we have come till here. This is our final wave equation for the transverse electric field. Okay. So then now we want to solve this for 3 different regions. Okay. So I'll say x equal to 0. So this is the x-axis, and sorry, sorry for the interruption. Um, so these are the, write it here. So this is my z-axis, this is my x-axis, and these 3 are the regions. So I will call this as x equal to 0. Above this it is the cladding, so it is refractive index NC. This is the film which is guiding the light, and this is the substrate, so NS. Okay. So in these 3 regions I have to solve for this particular equation, dou square Ey by dou x square plus k naught square ni square minus beta square times Ey is equal to 0. Okay. So here there are 2 conditions, right? Either beta will be greater than this or beta will be smaller than this number. So say my beta is greater than k naught ni. If beta is greater than k naught ni, that means this will be negative. So if this term is negative, then I'll just write it down, dou square Ey by dou x square right. Now this is positive, and I have put a negative side outside. Beta is greater than k naught ni. So yeah, so when my beta will be greater than k naught ni, then my equation will become like this. So this is like So like this is a standard form of an equation, and whenever we can write an equation in this form, we can write a solution to this equation. So you can just remember this for now. So the solution of such an equation, where this has to be a positive number. Okay, so solution of such an equation will be y of x equal to e naught, so that is the amplitude, and exponential of minus root of beta square minus k naught square ni square x. So x, because this is x, dou square by dou x. So yeah, so this will be a positive, this will be a real number, not a complex number, because beta is greater. And yeah, so we will have something like this as a solution. So mathematically we can also write plus or minus here, because uh, because negative and positive roots both. But if I write a plus sign here, then that will mean that the solution is solution will go on x, like with, as x goes to infinity, the solution will also go to infinity. So that's not a reasonable solution. So for keeping it physically reasonable, this is the only acceptable solution for beta greater than k naught ni case. Right. So only thing we have to assume here is that the solution of such an equation is this. Uh, so yeah, you can just verify it by putting it back. Yes. So similar thing we can do for the case for beta less than k naught ni. Again, we'll try to write it in this form with dou square ey by dou x square minus something times ey equal to 0, and then we can use this solution for it. So let's try doing it. So dou square ey by dou x square. This time, since beta, so this is already positive, but to write a solution in this form, I'll put a negative here. Okay, and then I'll make this as beta square minus k naught square ni square. However, now this quantity will be a negative quantity. Okay, or rather I can write it as, just to make things clearer, I'll write it as negative of k naught square ni square minus beta square. So now this is a positive number, but there is a negative sign. Y equal to 0. So then what will be the solution of this? Solution will be ey of x is equal to, similarly, just like this. So now some e naught prime need not be the same. E power minus root of this number. But root of a negative number will be root of minus 1, that is I, times root of so this is positive because of the condition. So yeah, this is our case 1, this is our case 2. Sorry, I forgot to put an x. So in case 1, we see that we get a exponentially decaying solution. So this is an exponentially decaying solution, right? Because this I can put it as some gamma. Then this is of the form e power e naught e power minus gamma x. In case 2, we are getting it as, sorry, this is case 2, we are getting it as oscillating solution. Like I can put this number as some kappa, then it is of the form e naught prime e power minus I kappa x. So now it is an oscillating solution. So yeah, so case 1 gives us a decaying solution. Case 2 gives us an oscillating solution. Okay. Now the question is, in which of these cases will there be case 1 and which case it will be case 2? Right. So my refractive indices are like this, right? So the film refractive index is highest, followed by the substrate, followed by the top cladding. Exactly. So if my beta is greater than k naught times nf, then that will mean that beta is greater than k naught ni for all the three cases, right? So if my beta, I'll repeat, if my beta is greater than k naught times nf, that will mean that it is also greater than k naught times ns and greater than k naught times or equal to nc, right? Because ns and nc are smaller than nf. So that will mean that all three regions have decaying solutions. If all three regions have decaying solutions, means there is no light, right? Because uh, as a function of x, for larger and larger x, if it's decaying here, negative x, what will be the thing? Like minus x. Yeah. Anyways, it will decay in all three regions, means there is no light confinement in any of the regions. Right. Either it can decay or we can have a plus solution here and it can grow exponentially. Both cases will be physically unreasonable. Because if it's growing exponentially, then we cannot have infinite energy. Yeah. So that is that. Then second case is if beta is less than k naught nf, but beta is greater than k naught ns or even k naught nc. So beta lies in between these two. Then what will happen? Then uh, wherever beta is greater than k naught ns and k naught nc, they will have decaying solutions. So they will be decaying here and here. However, wherever beta is less than k naught nf, so that is in the film we will have oscillating solution. So this is reasonable because it's not exploding to infinity in the substrate or cladding, and even in the film, and it's a oscillating solution in the film. So this is what we want to confine the light in the film and it should drop down to zero in the substrate and the cladding. So this is the desirable condition. So desirable condition is when k naught nf is greater than beta greater than k naught ns and k naught nc. So this is the condition for wave propagation in the film. Go ahead and I'll just write it down. K naught nf greater than equal to beta, sorry, So we found out one of the conditions for beta. So what is this beta? Just to remind you, this beta was the, sorry, I lost those notes. This beta was the propagation along the z-axis. So Ey of x comma z, I can write it as Ey of x times e power I beta z. So this beta is how it is how the wave is oscillating along the z component. So the propagation direction is z component, the confinement is in the x direction, and the electric field is in pointing outwards or inwards, anyways is fine, in the inside the plane. This is Ey. So that is the transverse electric case. Yes. Right. So now if this is the slab waveguide, say, here we have an cladding and film and substrate, then my propagation vector will be like this. It will keep bouncing up and down. My beta vector will always be pointing towards the direction of propagation, because by definition it is like that. And kappa vector will be the transverse component. So beta is called the longitudinal component. So the component that gives us the periodicity along the z, and kappa is called the transverse component. Okay. So just to remind you, kappa was basically this number. So in the case when I'll just write down the case 2 here again. Case 2 is when beta is less than k naught. So we know when it is less than k naught, it is less than k naught times nf, right? So beta will be less than k naught times n film. So in this case, that we will have oscillating solutions, and these oscillating solutions will be of the form some E naught times e power I minus I kappa x, where this kappa is nothing but, sorry, k naught ni square minus beta square root. Okay. If you remember, k naught is nothing but omega naught by c, and beta beta is our propagation longitudinal propagation constant. Fine. So this kappa is also related to beta. So basically we have the propagation vector, right? So beta is the z component of the propagation vector, and kappa is the x component of the propagation vector, wave vector rather. So that's why we will also have k square equal to kappa square plus beta square. Right. Now just I was saying, no. So for example, my just the analysis that we were doing here, if beta is less than like, so that if you look at it pictorially, if my beta is less than k naught nc, right? So if my beta is less than k naught nc, it will mean that it is less than k naught ns as well, and it's also less than k naught nf. So in this case, k naught nc and k naught ns are different. So that means the cladding ring index and substrate index are different. So if beta is less than this, that means beta is less than all the three. That means that there is a oscillating solution in all the three regions. Okay, so that means that the wave is not confined in the waveguide, rather it's present all over. The light amplitude is present all over. So this is not physical because it is not possible to have that much light. So if we are assuming that this is infinity in here and here, that will mean that we have infinite power in the waveguide, or rather the light is not guided at all and there is infinite power. So if you look at it in a ray optic perspective, that we can also think of it as one ray is coming, it gets refracted, and then it is transmitted ahead. So basically the light is allowed to stay in all the three regions. Okay, so there is no wave guiding that is happening here. In the second case, when it is between n naught c and n naught s, that means that in the substrate there are still beta is less than k naught ns. So in the substrate we will still have oscillating solution. Film we have oscillating solution, and in the cladding we have a decaying solution. That means decaying solution basically means, by now you are familiar, it will mean that it will be totally internally reflected. However, since here the light is allowed to propagate in this region, so then it will go inside the substrate, so it won't be totally internally reflected at this boundary. So for the light to be confined inside the film, we require that beta lies is smaller than NF, but it is bigger than both K naught NS and K naught NC. So for beta in this region, we have the desired solution where it is decaying up and down, and it's only confined in the film. Okay. So yeah, so if this is how my solution should look, how do I write it down mathematically? That is what we will do in the coming slide. We'll write this down mathematically, and we will ensure and we will find the different amplitudes by applying the boundary conditions. So until now we only said that it is of this form, right? So we have not found this E naughts yet, right? So we'll try to find those by applying the boundary conditions. So the boundary conditions will be that the electric field should remain continuous across the boundary. And second boundary condition is that magnetic field should also remain continuous across the boundary. However, since we are writing down all the equations in terms of electric field, we can use Maxwell's equation to convert the magnetic field boundary condition to the electric field boundary condition, and that becomes like, if you just do it, it will come out to be that dou E by dou X should be continuous across the boundary. So this condition is not inherently present, it is coming because of the continuity of magnetic field. Right. So first we have to write down the solutions in this region, this region, this region. So in the region where for x greater than 0, so this is my x equal to 0 plane. Okay, for regions for x greater than 0, I will have a decaying solution, exponentially decaying solution, that is given here. For regions between x equal to 0 and x equal to minus h, so this height is h. So for these regions I will have an oscillating solution given by this equation. So the b and c we have not determined yet, we are just keeping this a, b, c, d as constants, but I am just writing the form of the equation. And then for x less than minus h, that is in this region, we will again have a decaying solution, exponentially decaying solution. So this is the form of the equations for the solution of the electric field that we are expecting. So now let us start by applying the boundary conditions. So the first boundary condition across the boundary at x equal to 0. So say at this boundary, the first boundary condition is the electric field here should be the same as electric field here. At this point, the electric field coming from this equation should be the same as the one from this equation. So that means that a e power minus gamma c, because cladding, x is what? X is equal to 0. So the first boundary condition we are doing at x equal to 0 should be equal to b cos kappa f, because in the film, times 0 plus c sine okay. So now sine 0 is 0, but cos 0, like anything times 0 is 0, cos 0 is 1, so this will become b, and e power 0 is 1, so this will become a. So we already got b in terms of a, that is they both are equal. So let's try to find out c and d now, and try to write them again in terms of a. So this was for boundary condition 1. The second boundary condition is again at x equal to 0, dou e by dou x should be continuous. So that means that, what is dou e by dou x in this case? A minus gamma c e power minus gamma c 0 should be equal to, again, now we have to do dou e by dou x of this. Dou by dou x of cos theta is minus sin theta 0 plus c cos 0. So c equal to minus a gamma c by, so this is again 1. So gamma c by, oh I forgot to write a, there will be a kappa f2. So if you differentiate it first, there will be a kappa f term. Just differentiate it and check, you will get it. Correct. Okay. So now I am able to write c also in terms of a. Now only thing that remains is d. So to get d, let me apply the third boundary condition. Third boundary condition is at x equal to minus h, the electric field should be continuous. So let me just put x equal to minus h in this and this. So d at x equal to minus h, it will become e power 0 equal to, because minus h plus h is 0, equal to b is nothing but a only, a cos minus kfh plus c is nothing but minus a gamma c by kf kappa f sine minus kappa f h. Okay, so then that gives me d is nothing but a times cos kappa f h, because cos of negative is still cos, plus cos minus theta is cos theta only, plus gamma c over kappa f sine kappa f h, because sine minus theta is minus sin theta, so minus minus will become plus. Okay, so now I have got all the constants in terms of a. So based on that, I can write down my equations. So for x greater than 0, I can write down ey of x is equal to a e power minus gamma c x I hope you remember what this gamma c used to be. If we just go up, so this gamma is nothing but beta square minus k naught square ni square. So gamma c will be, similarly gamma s also. Okay. Okay. Yeah. So for x greater than 0, this is the thing. For x between 0 and minus h, we will have ey of x is equal to, b is again just a, e power, sorry, not e power, cos kappa f x plus c. C is nothing but minus a gamma c over kappa f into sine kappa f x. And for x less than minus h, ey of x is equal to d. Now what was d? D is nothing but a cos kappa f x plus gamma c over kappa f sine kappa f h. So this is d, and d into e power. So sorry, this is not, won't be x, this is h. If I write this as x, then it will again be an oscillatory solution. That's not the case. So this is h e power. We had found it here, right? This was h. I by mistake wrote it as x. E power gamma s x plus h. So nothing. I just wrote down these same equations that were here, but instead of a b c d, I wrote all the constants in terms of a. So then we get these set of equations. Okay, so this is the solution. However, the solution is still incomplete because we don't know what is kappa f, or right. So right. So we don't know actually what is beta. If we know beta, we can get to know what is all these gammas, gamma c or gamma s. We can know that if I know beta, and then if I know beta, I can also know kappa f. So I'll just write down those equations. So one is gamma c is this. Another one, gamma f, gamma s will also be root of beta square minus k naught square and s square. Hello? Yeah. And what is my kappa? Sorry. Kappa is nothing but square root of k naught square and f square, film square minus beta square. So in this case, beta will be smaller than this. Right. So yeah, so moral of the story is I am yet to know what are the possible values of beta, and also obviously the value of a. So a is just the amplitude that will depend on the intensity of light that I am sending in, but I still need to know what is the value of beta, so that I can know, um, so that then I can write down all these equations like I'll know the value of kappa f, I'll know the value of gamma c, I'll know the value of gamma s also, right? So then how do I find out the value of beta now? So to find beta, we apply the boundary condition 4, and so sorry. So the boundary condition 4 was basically at x equal to minus h, um, the dE by dx at x equal to minus h should be continuous. Okay. So let should be continuous. Okay, fine. Let's do it. Um, what does that mean? Let's differentiate this part. A kappa f sine so there will be minus, and then this kappa f x at minus h, so this will be a minus h here, so this minus and this minus will just cancel. I'm skipping some steps, you can try it on your own. Minus, if you can just keep this a also outside, minus gamma c cos kappa f h, sine differential is cos, and then cos of minus h will again be cos of h only. So this is my differential of this portion. Now I have to differentiate the other portion and equate them. So all this is a constant here, a and this entire bracket thing, so that will just come down like that, times e power this. So this we have to differentiate, that will be nothing but gamma s e power x will become minus h means 0, so that will be again 1. So after everything we will get, we'll just do it. So a I can cancel from both sides, and then if I just divide sine kappa f h, sorry, if I just divide by cos kappa f h throughout, then I'll get kappa f tan kappa f h minus gamma c is equal to cos kappa f h, I'm dividing it, so it will be 1 plus gamma c by kappa f, sine by cos is tan kappa f h times gamma s. So yeah, this is what we are getting. If you just simplify this, there's no space for me to do it, but if you just take the tan kappa h terms together uh, and rearrange it in some way, then like you will get an equation like this. So yeah, so there is already gamma s here, gamma s plus gamma c, and then you take the tan things together, and then basically rearrange it to get tan kappa f times h as gamma c plus gamma s upon kf into 1 minus gamma c gamma s by kappa f square. So basically what are we doing here? So this we got by simply applying boundary condition 4 on these equations. So from boundary condition 4 I get this condition that tan of kappa into h should be equal to this term. So now all these terms gamma c, gamma s, kappa f, all of them depend on beta. All depend on beta. So basically this is an equation. Using this equation we need to solve for beta. H we already know. So say we are solving it for certain geometry that is given here. So say my film refractive index is so much, 1.5, and then my cladding is 1.4 and substrate is 1.45, and the height of the film or the thickness of the film is given by 5 micrometers. So H is already known, the refractive indices are known, and the wavelength of light that I am sending in, that is also known. So if I know all these things, can I find the possible values of betas uh, from this equation? So turns out that is possible, and we can do it simply by using some numerical techniques. So I'll just write down all these things in terms of beta first, or in terms of kappa. So whenever we see such equations, right, the way to solve it is to plot. So we'll have a kappa f plot. So this is my kappa f x-axis, and then I'll plot tan kappa f. It will be a function like this, right? Keeps going from negative infinity to positive infinity, something like that. And then I'll plot the RHS. So RHS might be something like this. So I have actually done it in MATLAB. I'll show you just now. Yeah, I'll just. So as you can see here, I have defined what is NF, NS, NC, so the three refractive indices. I have defined the height or the thickness, and I have also defined the wavelength lambda. Right. Then what is my k? This is k is nothing but k naught, that is 2 pi by lambda, that is free space wave vector. Right. If this is my k and I am defining kappa from 1 to kappa max, or it could have been 0 also here, doesn't matter, or I can put a 0. Okay. So what will be maximum value of kappa? So the maximum value of kappa will be square root of k times nf square minus k times ns square. Okay. So this we are getting by, so okay, so if you remember what was kappa was nothing but square root of, we wrote it here, right, k naught square nf square minus beta square. And what is this beta? So this beta, if you remember, this for the solutions of this kind, the beta lies between k naught ns and k naught nf, right? So beta lies between okay. So what will be the maximum of kappa? The maximum of kappa will be reached when beta is at its minimum. So that will be k naught square nf square minus k naught square ns square. So beta is minimum at k naught ns, right? So kappa max should be this. So I'll plot from 0 to kappa max, kf max. Okay. So that is how I have defined this kappa max here. Then I have defined what is beta, what is gamma c, what is gamma s based on the equations that we just saw. And then I have plotted kappa. So look here, I have plotted kappa comma tan kappa into h, and I have also plotted kappa comma y2. So y2 is nothing but the RHS. I have written the RHS and then I have plotted the RHS as well as the LHS, and let us see how the plot looks. So now if you look here, so somewhere here is the maximum value of kappa that is allowed, and my LHS, that is the tan functions, so they explode to infinity like this. Okay, and the RHS starts at 0, goes to negative infinity, and then comes from positive infinity and then goes somewhere close to 0 but not exactly 0. Uh, right. So what are the solutions of the equation? The solutions of my equation are wherever my RHS and LHS are intersecting. So here, that is x equal to 5411, or x equal to, x is nothing but kappa equal to 5411, kappa equal to somewhere around 10921, kappa equal to 16335, and kappa equal to 21521. So you can say that 0 is also a solution, but that's like a trivial case, so we ignore that. So other than that, there are 4 solutions for my beta. So even though beta were allowed in anywhere between 0 to um, around 25,000 range, but still only 4 beta values are allowed based on our equation. So based on this equation that we have got, uh, so we have got this equation after applying the different boundary conditions. So for these particular boundary conditions, for these particular values of refractive indices and the thickness of the waveguide, I am getting 4 possible solutions. So 1, 2, 3 and 4. Okay. So from these 4 solutions, I can find out the value of kappa, right? So once I know the value of kappa, can I find out the value of beta? Right now, I can find out the value of beta once I know kappa. And once I know beta, I can also find out gamma C and gamma S. So since there are 4 values of kappa, that means there will be 4 beta values, which means 4 modes will be confined. So far we found out that there are 4 modes that are possible inside, and the only idea that we have about these modes is there will be uh, some decaying terms on the sides, and then in the center there will be an oscillating term. But how exactly will this oscillating term look? How exactly will it decay? How fast will it decay? So how fast will it decay, we can find out by finding out gamma C and gamma S. So for different values of beta, we will have different values of gamma C and gamma S. Right, so since we have 4 different values, 4 different modes, they will have 4 different shape of decay. And to find out this oscillating pattern, all we need to do is to substitute back in these equations. So you can see these equations, right? So now that we know what are the kappa f's that are possible, for the 4 different kappa f, if I just substitute back kappa and gamma, both gamma C and gamma S, then I will be able to get a pictorial feel for these different mode solutions. So for now we just found out that there are 4 possible mode solutions, but how do they look is what we need to find. So we can do it. So here we found out the different values of x, right? So these x are nothing but the kappa. So 5411 say is my kappa. So say my kappa is 5411. So from this kappa I can get beta. What will be beta? Beta is nothing but root of k naught square nf square minus kappa square. So just I inverted the kappa relation. So if I just solve this, what was k naught? So they have given us lambda, right? Lambda is 1 micrometer. From lambda I can find omega naught. Once I know omega naught, I can find k naught. They have already given me nf. Kappa is what I found out just now is 5411 for the first mode. Based on that, I can find out beta. Now this beta, I can, so now that I know beta, I can plot the different modes. So once I know beta, all I need to do is, I need to substitute for, so once I know beta, I can know kappa f, gamma c, and gamma s, and then I just need to substitute. So a is the only unknown that is left. That will depend on how much light we are pumping in, but the shape of the mode, that we can know by knowing the beta values. So the 4 beta values that were allowed in this case are shown here. So for these 4 beta values, we will see mode shapes like this. So this is my x-axis, okay. So this is x equal to 0. Beyond x equal to 0 um, is my cladding. So here it is cladding, here it is substrate, and in this region from minus 5 to 0 it's the fill. And you can see that the plots are slightly skewed towards one side. And that's because the cladding index is not the exactly same as the substrate index. So the yeah, so that's why it's not exactly symmetric shapes. Slightly asymmetry is there. Yeah. So that's how the modes look. So next is so we can do all this analysis to find out the number of modes in a waveguide, but is there a easier way to predict how many modes will be present? So if you remember, this was the plot, and we plotted it till kappa max. Now look at these tan functions. So the tan will explode to infinity at tan x equal to pi by 2, at 3 pi by 2. So this gap is pi, and then 5 pi by 2, like that. So it will explode to infinity at these points. So based on how many tan functions, tan of kappa times h, how many times it becomes pi by 2 or 3 pi by 2 or any odd multiple of pi by 2, that many times it is possible that it will cut my RHS side. So it's just approximate. It might happen that it can be one or one mode here and there. However, if I just find out the integer, um, so if my number of modes is approximately integer h times kappa over pi. So whenever kappa h becomes pi, so this is 1 pi, say somewhere here, right? Whenever it becomes pi, there is a high chance that we have a one mode. When it becomes 2 pi, there are two modes. When it becomes 3 pi, there are three modes. 4 pi, four modes, like that. So yeah, so the number of modes that are confined depend critically on kappa max and h. So when if kappa max was small, then the number of modes that would have been confined would be less. If my h was small, then if my h was such that there were only two tan functions here, so if my h was small, that means that kh becomes pi very slowly. So then there are only two times that the tan h function cuts. So then my number of modes will be 2, like that. So it will depend on kappa max and h. So the number of modes will be approximately integer of h times kappa upon pi, or sorry, kappa max upon pi. So that is nothing but integer. Just now we had seen, right, what is kappa max. Kappa max is nothing but root of k naught square nf square minus k naught square ns square. I'll we can simplify this. Integer of h k naught square is there in both the terms, right? So root of nf square minus ns square upon pi. So if you remember the first lecture of first or second lecture, we had seen that this number is nothing but the v number. So today we define this as a v number. V number is nothing but k naught h root of nf square minus ns square. Okay, the k naught is nothing but omega naught by c. So whenever v number becomes, or rather we can say the number of modes is nothing but v number upon pi, or the closest integer smaller than v number upon pi. So that is how the concept of v number has come from this equation here. But obviously to get a more accurate understanding, it's better to always plot this tan kh equal to gamma c plus gamma s upon basically this transcendental equation. We need to plot it and then find out what are the solutions, where, or rather where, at what points my LHS and RHS are overlapping. So the number of points where it is overlapping except the 0 point are the number of modes. Okay, so that's it for today. Yeah, we can continue our discussion in the on the coming Friday.